to engineers mindset. So in this video, we are going to be looking at how to draw the shear force and bending moment diagrams for a simply supported beam carrying the point load. So we are given this beam on the board and we are asked to draw the shear force and bending moment diagram. Our first task will be to find the support reactions at A and at point C. Okay, so we have to first of all start by drawing our free body diagram. Alright, so FPD simply means free body diagram. So you pull down your beam. Now this support here is a pin reaction, and for every pin reaction we have two types of support or two types of reaction at a pin support. We have the vertical reaction and then we have the horizontal reaction. So at this point where the pin support occurs, we have a vertical reaction. You can simply call that RAY. Y indicates vertical. Then we have a horizontal reaction. You can simply call that RAX. So X there simplifies horizontal. So A and A simply means point A or joint A. Now at point B we have a 50 kilonewtons force acting down there. So you indicate that 50 kilonewtons. And at point C we have a roller support. So whenever you see your support reaction in this form with these roller balls under, that is actually a roller support. Now the difference between a roller support and a pin support is that a roller support has just a normal reaction, one reaction that is normal to the surface. Normal simply means that the reaction is at 90 degrees to the surface where it is occurring. Okay, so for a horizontal beam, you always have the roller support to be what? A vertical reaction. But if the beam was to be a vertical beam, it simply means that the roller support will have what? A horizontal reaction. Okay, so every roller support must always have one reaction which is perpendicular or at 90 degrees to the point where it is occurring. So since this beam is horizontal, it simply means this reaction here will simply have a vertical reaction. So because it makes an angle of 90 degrees with the point of occurrence or with the point where it is acting. So it is actually different from the pin. Pin is always going to be vertical and horizontal. So if a pin occurs on a vertical beam, it still maintains vertical and horizontal reaction. But if a roller occurs on a vertical beam, the roller support or the reaction of that roller becomes what? A horizontal reaction. But if it occurs on a horizontal beam, the reaction becomes a vertical reaction. Okay, so this is point C. So our reaction here, since it's vertical, you simply call this RCY. This becomes now the free body diagram of that system. So our idea now is to find RAY, RAX, and RCY. You can do this using two approaches. You can either use the moment equilibrium equation. So you just simply apply moment at point A, obtain RCY, then apply moment at point C, obtain RAY, and you're good to go. Or you can simply use the moment equilibrium equation and the force equilibrium equation to actually achieve the same result. Okay, but let's use the force equilibrium equation and moment. So remember, distances apart. This is point B. Distance is 2 meters apart. You have here also 2 meters apart. So the first is to employ our force equilibrium equation, which states summation of vertical force is equal to 0. So you consider vertically upward force to be positive, vertically downward forces to be negative, right? So you look through the beam, add up all the vertical forces on the system or on the beam. I have RAY pointing vertically upwards. Since it's upward, we consider it to be what? Positive from our equilibrium equation. Okay, so you simply have RAY positive. Now the 50 kilonewtons force is acting downwards, so you consider it to be what? Negative, right? So it becomes minus 50. Okay, then finally RCY is pointing upwards, positive, plus RCY. The law simply says summation of vertical force equals 0. So you simply equate this to what? 0. Okay, so simply because you have two unknown variables in one equation, it means it's very much impossible to solve, right? So from here you can simply say RAY plus RCY is equal to 50. So you can simply call this equation 1. Okay, now the next equilibrium equation we'll take is simply what? Our moment equation. So you can simply take moment at point A or you take moment at point C. Now whichever you do, you're going to be very correct, right? Taking moment at any of the points will always give you the other reaction. So let's simply take moment at point A. The moment of a force about any point is equal to 0. So if you take moment at point A, that simply means the moment of this force RAY and RAS about this point A becomes automatically 0. because moment is the product of force and the perpendicular distance the force makes about the point, right? So if this force is ray and rax is occurring at point A, it means that it does not have any perpendicular distance about point A. The both forces are simply at point A, so their distance about point A is 0. Therefore, their moment becomes their force multiplied by distance, which is now 0. So the moment of these two forces about point A becomes 0. The same thing happens if you take moment at point C. It means that the moment of RC about that point becomes 0. So that's why I said in the first, when I said the explanation, I said you can use two ways to actually obtain these reactions. You can simply take the moment equilibrium equation. Taking moment at point A, that will give you RCY. And then you take moment at point C, that simply gives you RAY. But let's just go on and take a moment at point A, right? So summation of moment at A is equal to 0. We consider clockwise moment to be positive, and then anti-clockwise moment we consider it to be negative. So we are simply taking moment about this point, right? Now the moment of this force, the 50 kilonewtons force about this point, this force is pointing downwards, which means this force will turn in this direction to take moment at point A. And if you take a look at this direction is a clockwise direction, and we say let clockwise moment be what? Positive. So it means the moment of this force about point A becomes positive, and the total perpendicular distance it takes this force to get to point A is simply 2 meters. Therefore, the moment of that force becomes 50 multiplied by 2. Again, this force will take the moment of RCY about point A. This force is pointing upward, so it simply means this force will turn in this direction to take moment at point A. Now, this direction is simply what? Anti-clockwise, as assumed here. So it means the moment of this force about point A becomes what? Negative. And the total perpendicular distance it takes this force to get to point A becomes total distance of the beam, which is 2 plus 2, and that's 4. So you simply have minus RCY multiplied by 4, and this is going to be equal to what? 0. So with this now you're able to find RCY. Okay, so let's do this and see. Now 50 times 2 simply gives us 100 minus 4 RCY is equal to 0. So from here you simply have that 100 is equal to, let's send negative 4 RCY over here. Negative sign cross and equal to sign becomes positive, so you simply have 4 RCY, and therefore it means the vertical reaction at point C becomes 100 divided by 4, which simply implies that RCY is equal to 25 kilonewtons. So having found RCY, you simply plug in the value of RCY into equation 1. If you do that from equation 1, you simply have RAY plus RCY, and now RCY is simply 25, and that's going to be equal to what? 50 from equation 1. RAY plus RCY equals 50. So you simply make RAY subject. This simply implies that RAY becomes what? 50 minus 25. So if positive 25 crosses over here, it becomes negative. So you have 50 minus 25. So this simply implies that RAY is going to be equal to 25 kilonewtons. So we have now the two reactions. Now let's try to use the moment method and see if we are still going to obtain the same reaction. So mind you, we're taking moment at point A and we've gotten RCY. Let us now take moment at point C and see if we're going to have RAY to be this same result. So if you're taking moment at point C, remember it's now going to be summation of moment at point C equals 0. Let's also consider clockwise moment as positive, anti-clockwise moment as negative, right? Now RAY is pointing upwards, so moment of this force about point C will turn in this direction, okay? And this is going to be what? A clockwise direction. So we said let clockwise be positive, so this is actually going to be positive. Total distance it takes this force RAY to get to point C is the total length of the beam, which is 2 plus 2, and that's 4. So you simply have RAY multiplied by 4, okay? Then you take the moment of the 50 kilonewtons force about point C. This force is acting downwards, which means this force will turn in this direction to take moment at point C. And what direction is this? Anti-clockwise. So it simply means you have minus 50. Total distance it takes that force to get to point C is actually what? 2, and this is going to be equal to 0. And then you see this is going to be 4 RAY minus 50 times 2, there is 100 equals 0. So 4 RAY equals 100, and therefore you also find RAY to be equal to 100 divided by 4, and that gives us 25 kilonewtons. So you can either simply use the moment to moment approach, right, and then avoid using the first equilibrium equation. Just use moment to moment and you will still obtain the same result. You can see RAY gave us 25 kilonewtons, same as RAY here, 25 kilonewtons. Okay, so first task achieved. We've gotten the reactions. Now the next thing to do is to carry out our shear force analysis and then our bending moment analysis. Then we can proceed to what? Draw the diagram. Okay, so but just before we proceed, we have one more force there, which is RAS. So one of the equilibrium law for force simply states that summation of horizontal force f of x is equal to what? 0, right? So you sum the entire forces, horizontal forces, and equal to 0. So throughout this beam, the only horizontal force that we have here is simply RAX. So this simply means that RAX is automatically taken as 0, just in case you're wondering. Okay, so I just have to explain this. All right. Okay, so let's start our shear force analysis. Shear force analysis. Now, shear force simply means the stepwise summation of the entire force acting on the beam from beginning of the beam to the end of the beam, considering vertically upward force as positive and vertically downward forces as negative, right? So you're simply going to sum the entire force from the beginning of the beam to the end of the beam at each point of the beam. So you start from point A, shear force at A. So this simply means the force existing at point A. So you look at point A, remember we said RAX is simply 0. Okay, so remember, so this force is off, the value is 0, so you simply take it off. Now the only force at point A is RAY, and this force is pointing vertically upwards. The magnitude is 25 kilonewtons. Since it's pointing upwards, it's taken as positive, right? So it means some shear force at A is simply 25 kilonewtons. Next, you move now to point B. So this is the scope now. This 25 kilonewtons force moves down to point B initially. So what you do is simply what? Shear force at B prime. B prime simply means initially. So what we still have is this 25 kilonewtons force moving to point B. So you still keep it there as 25 kilonewtons. Now on getting to point B, the force now encountered a downward force of magnitude 50 kilonewtons. Remember, if the force is acting downwards, you take it as what? Negative. So you simply call that shear force B prime prime, which means finally at point B, this 25 kilonewtons force encountered a downward force, so minus 50 kilonewtons, and this is going to give us what? Negative 25 kilonewtons, and you have this. Again, this negative 25 kilonewtons force now move from point B down to point C, again initially. So you simply say shear force C prime, which means initially at point C, the value still remains what? Negative 25 kilonewtons. But on getting to point C, it now encounters an upward force of magnitude 25 kilonewtons. Remember, upward, that means it's going to now be what? Positive, right? So you simply indicate it here. Now you call that shear force C prime prime, which means finally at point C, this negative 25 kilonewtons force experienced an upward force of 25 kilonewtons force. The value becomes now what? 0. So always keep it in mind. At the end of every shear force analysis, you must always have 0 as a result, which shows that the beam is in what? Equilibrium. Okay, so after the shear force analysis, let's move on to the bending moment analysis. Bending moment analysis. Okay, bending moment analysis. Okay, so from equilibrium equation, the moment of force at every point on a beam is 0. So that means, remember, bending moment once again is a summation of the entire moment action on a beam from beginning of the beam at each point of the beam to the end of the beam. Not forgetting, the moment of a force at any point of the beam is 0. So you start from where? Point A. okay, moment of this force about point A automatically is 0 because there is no distance between this force and point A. So it's simply point A, 25 kilonewtons force is already at point A, no distance to point A, therefore its distance is 0, and moment is force times distance. Since the distance is 0, it simply means the moment of this force about point A becomes 0. So that being said, the bending moment at point A is automatically what? 0. You keep it. Now, moving from point A down to point B, the same ideology. The moment of this force, 50 kilonewtons force at point B, about point B is 0. But there is another force that can take moment about point B. That force is the 25 kilonewtons force, because now we have moved past point A down to point B. This force now has a distance about point B. But the moment of this force at point B, which is the 50 kilonewtons force at point B, becomes 0 because this force is already at point B. There is no distance between this force and point B. The only force now that has a distance to point B is the 25 kilonewtons force. Once again, since this force is pointing upwards, always take its moment as positive. So when doing bending moment analysis, if the force points upward, consider the moment of that force as positive. But if the force points downward, consider the moment of that force as negative. So the moment at point B now becomes simply 25 times total distance it takes this force to get to point B, which is 2. So moment, bending moment at B equals 25 multiplied by 2, and that is simply 50 kilonewtons meter. You have that. And finally, you take moment at point C. Moment at point C, again, the moment of this force, 25 kilonewtons force, that is RCY at point C, is 0. But behind point C, we have two forces. 25 kilonewtons force from point A, and then 50 kilonewtons force from point B. These two forces have a distance about point C, so they can take moment about point C. So the moment of this force about point C becomes 25 times total distance it takes this force to get to point C, which is 2 plus 2, that's 4. And since this force is pointing upwards, it means it's going to have a positive moment about point C, right? Okay, so you simply have bending moment at point C becomes first 25 times 4. Next, since this force, which is at point B, 50 kilonewtons force, is acting downwards, like I said, if a force is acting downwards and you're doing bending moment analysis, it means that the moment of that force about that and any point you're taking moment now becomes what? 0 and negative, please. So it means this is going to have what? Negative 50 times total distance it takes this force to get to what? Point C, which is 2 meters. So you have minus 50 times 2. So this is going to be equal to 25 times 4 is 100 minus 50 times 2 is also 100. So this simply means bending moment at point C is equal to 0. Again, at the end of every moment analysis, the result is always going to be 0, which shows that the beam is under what? Static equilibrium. Okay, now we are done with our analysis. The next thing to do is to plot the diagram. So in order to draw a diagram, let's just simply make a simple sketch. Trace all the points, the outlines from each point. You can do that with broken lines. So we're going to basically do a freehand sketch of the diagram, which is actually permitted. Now the first diagram will be the shear force diagram. So you look at the highest value of the shear force. So you have 25 kilonewtons. Okay, highest value remains 25 kilonewtons, right? So we'll have lowest value as well is negative 25. So you can simply draw a straight line here. Okay, so this represents positive 25 kilonewtons and this represents negative 25 kilonewtons. So you draw this point out, trace out each of the points, and you trace out each of the points. So this is the 0 or the origin line, this is the origin or the point of 0, right? So you start. The first is moment shear force at point A. The value is 25 kilonewtons. This is line A. So from the origin, shear force at point A is positive 25. You place an asterisk here, and you have it. The next is shear force initially at point B, still 25 kilonewtons. So initially at point B, so this force moves initially at point B. So you have it here, still 25 kilonewtons. This is point B, and this remains 25. Then finally at point B, shear force B prime prime, which indicates finally at point B, the value is negative 25. So finally at point B, this is negative 25, this is point B, so this is where it meets. You simply what? Asterisk it, and you have that. Then shear force at C, initially at point C, still remains negative 25. So from point B, this is now point C, initially still negative 25. So you asterisk that point. And finally at point C, shear force C prime prime becomes 0. So finally you have it here as 0. So you asterisk and keep there. So what do you now do? The shear force diagram, you start from the origin, remember? So you start from the origin. The shear force diagram for a point load is simply a straight line that connects each of the points, a straight line. So starting from the origin, you have a straight line first, connect each of the points. A straight line, connect each of the points. Straight line, connect each of the points. Straight line, connect each of the points, and then connect each of the points. So this diagram here represents the shear force diagram for this given simply supported beam carrying a point load. So here is our shear force diagram, and you have this. The next is to draw the bending moments diagram, right? So you take a look at the bending moment analysis, which is your highest value and which is your lowest value. My highest value from here is 50 kilonewtons meter, and my lowest value is simply 0. So you simply draw a straight line, okay? Straight line. So this is the origin, 0, 0, 50 kilonewtons meter. You can simply take it here. So this is our 50 kilonewtons meter. So you trace out this point, okay? So you start, moment at point A is 0. This is line A. This is the origin. So you asterisk here 0. Moment at point B is 50 kilonewtons. This is line B. This is 50 kilonewtons meter. You asterisk where they meet. Finally, moment at point C is 0. This is line C, and this is 0 mark. This is where they meet. You simply asterisk that point. Okay. Now having found this, you now connect the bending moment diagram for a point load. Remember, these are all point load. Is a slant line that connects each of the points. The bending moment diagram for a point load is simply a slant line that connects each of the points. So you simply slant the line and connect each of the points. So from the origin, you slant, connect to this point, you slant, and you connect to this point. This represents the shear force bending moment diagram for that given question. So these are bending moment diagram. All right, guys. So that is how to draw the shear force and bending moment diagram for a simply supported beam which is carrying a point load. In the next video, we are going to be looking at the shear force and bending moment diagram for a simply supported beam which is carrying a uniformly varying load. I'm sure you want to be a part of that video, so do well to tap the subscribe button right now and turn on your bell notification so you don't miss out on that video when it drops. In the meantime, do well to like this video, comment nicely, share to your friends. I will see you in the next video. Cheers.